the sector of a circle shown at left, I pasted it up here, has center at point O. The radius of the circle is 5. So we see we have part of a circle right over here. So we have that arc AB, and you see the radius from the center to any point on that circle. So OB is 5. And the length of chord AB is 6. And they've labeled that from A to B. The length is 6. Line segment CO, this is CO, is perpendicular to line segment AB. And they've labeled that for us as well. What is the length L of line segment CO? What is the length L of line segment CO? So one thing that might immediately jump out at you is we are dealing with a right triangle up here. So if you have a right triangle, if you know two of the sides of a right triangle, you can use the Pythagorean theorem to figure out the third side of the right triangle. And so let's see, if we knew what CB was, if we knew the length of segment CB, so let me pick an appropriate color, I'll do blue. So the Pythagorean theorem would tell us that the length of segment CB squared plus L squared, I'll do plus, let me do L, I'll just do it all in this, plus L squared is going to be equal to the hypotenuse squared, is going to be equal to 25. But we don't exactly know the length of segment CB just yet. It's tempting to say that it's 3. It looks like it's half of the 6, but we don't know that for sure just yet. What we do know for sure is, look, if this is a right angle, then this is going to be a right angle as well. These two things are supplementary to each other. They're going to add up to 180, so this is going to be a right angle. And if this side right over here that has length L, it's common to both of these triangles, to this triangle up here and to this triangle down here. Now the other thing that we know about this triangle down here is that AO is also going to be a radius of the circle. It goes from the center of our circle to it actually sits on the circle, on kind of the outside of the circle. So this is a radius, so this is also going to be 5. So what's the length of AC? Well, we could use the same idea. We can relate AC, L, and 5. So we could say just by the Pythagorean theorem, the length of segment AC squared plus L squared is equal to 25. So when you see it in these terms, you see very clearly that AC is going to be equal to CB. In fact, let me make that a little bit clearer. So we could say, if we subtract L squared from both sides, that CB squared is equal to 25 minus L squared. And we could write that AC squared is equal to 25 minus L squared. And so these two things are going to be equivalent. So this is going to be equivalent to that right over there. Now that is useful because now we know that the point C is at the midpoint of AB. And so these AC is going to be half of the 6 and CB is going to be half of the 6. And now we can say with certainty this is going to be 3 and this is going to be 3 right over there. Now once again, you might have immediately jumped to that conclusion and you would have gotten the question right. Or you could have kind of jumped to it a little bit faster without having to write all this math. You could say, hey, look, you know what? I have two right triangles. I know that two of their sides are the same, so the third side has to be the same as well. So this is going to be the same as that, and so they're each going to be half of the 6. But that's all you need now to actually solve for L. We can say that 3 squared plus L squared is equal to 5 squared. Or we could say 9 plus L squared is equal to 25. Subtract 9 from both sides. L squared is equal to 16. Take the principal root of both sides. L is equal to the square root of 16. The principal root of 16, L is going to be equal to 4. And we see that choice right over there.